as well, I would like to thank a lot of participants who made this conference so great by participating in all these lively discussions, which were animated but never not collegial. So in the memoirs about the golden days of physics, you can often read about description of some schools where every discussion was a science fiesta. I think this is a very fair characterization of our conference, so that's why I'm very grateful for people who organized it. This work was done by me and Yaroslaw Bazaliy. I am at the University of South Carolina, was in the University of also here in France. Both universities are in the south. This is south of North America, and this is south of France. Much better. And the subject I'm going to talk about are pure spin currents and their consequences. This is my outline. I will be talking about a very simple and old-fashioned way of generating spin currents. Although it is old and well known, I think there is a surprise which we found, and it's a fun example of new things that are possible. So I'll talk about the injection of pure spin current. Pure spin current is when spins are moving, but there is no motion of electrons, or electrons move in left and right directions with the same rate, but do not transmit any current. And it started a while ago, and after that, after the original proposals, there were many other much more fancy ways to inject pure spin current. But I'll be talking about this one where you have a ferromagnet and a normal piece, and you pass the current through this junction. And then because in the ferromagnet there are more spins ups and spin downs, you expect that they will be dragged by the current into the normal metal, and there will be an imbalance, which is non-equilibrium. Note, that's important, that while it's true that there are more spin currents in the ferromagnet, there are more spin ups and spin downs in the ferromagnet. If you just connect them but do not pass an electric current, there will be no extra spin in the normal metal. So there is no proximity in this sense. It's only a non-equilibrium effect when the current is going. So in order to describe it, I will use a very simple model, which was, comes to us from the 60s, and then mostly known to quantum spintronics from this paper by Bazaliy and Ferret. But this model assumes that electrons move diffusively, and so this is my picture of many electrons inside the normal metal. The red arrows are their spins. Some of them have spins up and some of them have spin downs. The mean free path is very short. I can apply diffusive equations. And then the second assumption that the spin flip time is much longer than momentum relaxation time. So if I mentally separate the set of all electrons in the subset of spin up electrons and spin down electrons, then the collisions which transmit an electron from here to here by flipping the spin are very rare. So as a result, I can think about the spin up and spin down electrons as two separate Fermi gases. And the equilibration within each of those gases is fast, but the equilibration between them is much slower. In the non-equilibrium state, therefore, I can have a regime where this gas is equilibrated. It is characterized by a certain number of particles and up, and this gas is equilibrated, but there is no equilibrium between the two. In the language of this energy diagram, that would mean that there are two separate chemical potentials, one for spin down and the other for spin up electrons, and they're both different from the thermodynamic chemical potential μF, which will be achieved if you wait for a long time until everything has relaxed. So this is I will discuss the situation with metals. So here the deviation from equilibrium of the total number of electrons is proportional to the deviation from the equilibrium Fermi potential, and therefore in all linear equations I can more or less interchange this difference by this difference, and that will just lead to multiplication of other constant by the density of states nu. This picture is qualitative, and this is for a normal metal. Now I will remind people who know and describe for people who do not know the diffusive equations themselves. They are very simple. As we discussed, in this model we have two gases, and therefore there will be two currents, one for spin up electrons and the other for spin down electrons. And these spin currents are given by diffusive equations through the gradient of spin up, the chemical potential up and chemical potential down. In the normal metal, the diffusion coefficients for both up and down are the same. If you are in a ferromagnet, then you have two different diffusion coefficients, and you can introduce the polarization of current P, which measures how different they are. Then the diffusive equation looks like that. The change of M is due to the divergence of the corresponding current, plus the flip. This is a rare event we were describing in the previous slide. Flip from spin up to spin down and vice versa. The rate of the flip, again, will be taken in a very simple minimal model, proportional to the difference between the densities or the difference between the chemical potentials. You can work with this equation, but it is very often more convenient to work with total current, which is the sum of spin currents, and the spin current, which is a difference of two currents. Then you can convert these expressions to those expressions in the box, where the electric current and the spin current are described as through the gradients of the average potential. This average potential is actually the potential which a voltmeter would measure if connected to the metal, and the spin potential, the difference between the two spin currents. Both gradients are coming into expressions for those currents. Those diffusive equations, for the third equation, can be now closed by saying that the divergence of electric current has to be zero, and the divergence of spin current is related to how fast the spins are flipped, and that is, in our simplistic model, just the relaxation time effect approximation, and mu s divided by the spin flip time. Then you find two equations for mu and mu s, and note that the equation for mu s is decoupled. So in many problems, you don't even have to think about the equation for mu, just solving this second equation. The characteristic length which appears is the diffusion coefficient times tau s. That's how far the spin can travel on average before it is flipped. The standard application for this equation is the injection of current from a ferromagnet to a normal metal, and indeed, if you solve them with the boundary conditions that are appropriate for a transparent interface, you find that the spin current is, which is constant in a ferromagnet, where there is a constant spin polarization, decays when it comes into the normal metal. Then we find that in the normal metal there is an accumulation of spins, which persists on the length of lambda s. The current on the previous slide is a combination of both electric current and the spin current. So how should I get the pure spin current without electric current? This issue was pushed forward by Johnson and Silsby many years ago. And in their paper, they succeeded in producing pure spin current by injection and also detecting the pure spin current. So their device is here. There is a pair of electrons, ferromagnetic and non-ferromagnetic, normal metal, and another pair of ferromagnetic and normal metal electrons. You inject the current here, and you extract it from here, so the electric current flows in this part of the device. The right-hand side part of the device is electrically disconnected, and so the picture shown on the left is a cartoon of how electric current flows from the injector here to the left, but spin current, which is driven by both the voltage and the gradient of spin potential, will flow in both directions, because as you inject spins here, you have an extra many spin ups as opposed to spin downs. You have this spin accumulation right under the contact, and then this spin accumulation diffuses in both directions, so it diffuses towards the other electrons. what Johnson and Silsby found that you can detect the fact that there is spin current by measuring the voltage between the non-ferromagnetic and ferromagnetic electrons. If you would measure a voltage here between two non-magnetic electrons, you would always get 0 because there are no electric currents. But between the ferromagnet and the normal metal, you get voltage which is proportional to the current that you inject here. This is called the non-local resistivity. You'll have current flowing here, the voltage is measured here, but they are related with an Ohm's law. The non-local resistivity will also depend on whether these two guys are parallel or antiparallel, and we will see in the next slide why this is the case. So Johnson and Silsby had an argument which they based on thermodynamical considerations, which gave them the value of the voltage, and their answer is correct. And the answer is correct, but it's sort of more satisfying to discuss it from the point of view of those non-equilibrium equations rather than from sort of a dynamical point of view. And the explanation, the explanation of their result is like that. We take the equations for the currents in terms of the gradients of the electrical or electrochemical potential and the spin potential. And we look at the electrode, the ferromagnetic electrode, which is located here. This is a side view, the cartoon of this electrode. As the spin current is injected from the left, it goes and decays along the way, but some spin current reaches this point and produces here some spin accumulation, which I will call μs of 0. This spin accumulation diffuses forward, but it also starts to diffuse up. So in the vertical ferromagnetic contact, there is a gradient of spin accumulation, gradient of μs, and therefore, if I want to write down the total current inside of the vertical ferromagnetic contact, this is going to be my formula with the derivative along y, and because the whole right-hand side is a disconnected element, the electric current doesn't enter it, it doesn't leave it, therefore the electric current here has to be equal to 0. So the left-hand side is 0, and therefore any gradient of μs should produce the balancing gradient of the chemical potential, and therefore you expect that there will be a difference between chemical potential here and here. And this is the voltage, mu is the voltage which you measure, so the difference in mu here is your voltmeter reading. Now, in general, everything depends on how these gradients behave as a function of the height, but if you go far, if the height of this electrode, Tf, is large compared to lambda s, then we can be sure that μs, which is not 0 here, is already 0 here because of spin decay, which happens everywhere. So you can integrate this formula, and you can find out that the total change of mu between this point, or this point, and this point, is equal to the total change of μs, and the total change of μs is equal to μs 0, because μs decays somewhere here in between. So as long as Tf is big compared to the spin diffusion length lambda, you expect to measure always the same voltage independent of Tf. And this voltage can be found from this equation, and that's the result. That's the Johnson-Silsby result. It depends on material properties, the spin polarization inside the ferromagnet, and on units. So Johnson-Silsby said, look, we measure the spin accumulation, which is a result of spin current. This is our spin voltmeter. It measures spin potential. You can look at it two ways. If you know μs, you can measure the properties of ferromagnet, the polarization. If you know already what kind of ferromagnet you're using for this electrode, then you can measure the spin potential. As you have noticed, a lot here depends on the fact that this is an electrically disconnected part, and so no current is flowing in. Now, in practice, of course, people produce devices with different types of ZF electrodes. Sometimes the electrodes are narrow, like in my previous picture, and sometimes they are not so narrow. And if you have a not so narrow electrode, you have a logical question arising. Well, here I know that the voltage is just proportional to the spin accumulation here under the electrode. here what happens is the spin accumulation here is going to be different than on the other side, because spin current is propagating, it is decaying along the way, it's not conserved. So μs here are different. Which one should I use in the Johnson-Silsby formula? And this is a question which motivates what is going further after that. People were worried about it because they do have wide electrodes, and this is a paper where people were simulating their device. They were taking the Bazaliy equations, solving them numerically. They were obtaining the pattern for the electric current. So this picture is a top view of the actual device. Two ferromagnetic electrodes, a normal electrode under them. The arrows signify the current. So the current pattern is actually complicated. The current, which was nominally supposed to go inside here and then be collected over here, actually, of course, mostly goes to the left, but then it also goes a little bit to the right. There is a dashed line here which separates the normal view and magnified view. So the length of the current arrows here on the right-hand side is significantly magnified compared to here. There is a small current which actually goes here to the right and then comes back. So for the purposes of this device, this is a fine simulation. But what it shows is that the voltage, the Johnson-Silsby voltage, actually depends on the position of your electrode on the ferromagnetic layer. And even if the ferromagnetic layer is thick compared to the spin diffusion lengths, you still have the position dependence. Then you look at your equation and you say, well, if mu is different to different points, then I should have either the gradient of µs, which is not zero, or I have to have electric current, which is not zero, no other option. Having non-zero gradient of µs far from the spin injection point, much further than the spin diffusion lengths, is strange. Having electric current in an electrically disconnected device is also kind of strange. So which one of those two options is realized? Now, certainly, and I will argue that this is the fact is that the electric current is flowing. So I will say that, I will start with saying that, of course, inside an electrically disconnected device, you wouldn't have a current which starts on one side and ends up somehow on the other side, but you still can have a current which goes in a closed loop. Think about a piece of metal which is placed in the variable magnetic field, which generates eddy currents inside of it, and you have those electric currents flowing in an electrically disconnected device. So this slide gives a proof that in the case when you have this heterogeneous structure with ferromagnet and normal metal, you are bound to have those loop currents, loop electric currents generated inside of the disconnected part of the device, provided some conditions are satisfied. Now, if you go back to my equation over here, and you look at this equation for electric current, you can develop a way to think about it. You can say, well, this is just the standard gradient of chemical potential, and this is extra thing, and I will think about this as an effective electromotive force. So gradients of µs provide effective electromotive force for the equations, for the electric current. If I knew gradient of µs, I would know this force, and I would be able to calculate the currents. And let me think about how these gradients are distributed in the device, where I have two layers, the normal layer, the ferromagnetic layer, and I inject pure spin current here from the left. Then the spin current will diffuse everywhere, maybe with different rates, but inside of the normal metal, the polarization is zero. The polarization is zero, so the effective EMF doesn't exist in M. And it exists in the ferromagnetic layer. These arrows show my effective EMF, and so my intuition would be that, look, this is just a circuit. I have an EMF here, and so there will be no surprise that this EMF generates a current going around the circuit. Now, can I prove it more formally? And this is a proof. Since currents, loops of currents mean the curl of something is non-zero, I will calculate the curl of J divided by D. D is a diffusion coefficient, which is material dependent, so there is a jump in my particular device. There is a jump of D between normal and ferromagnetic metal, but this formula can be applied to any situation when D changes continuously or whatever. But I'll take this curl, I'll calculate it using my expression for the current, and I'll get this formula. So it's a gradient of current polarization, vector product with a gradient of the spin accumulation. If this vector product is non-zero, then the curl of this guy is non-zero, and the only way to have non-zero curl, I mean, you would never be able to have non-zero curl if the electric current in this part was zero everywhere, because you would be taking the curl of zero. D is a positive number, so you never divide by zero. And so the theorem is that if the vector product is non-zero, then there will be an electric current, no other way around it. In my particular device, P has a gradient exactly on the surface, so the gradient of P is perpendicular to the surface, and the gradient of US is determined by the diffusion of spin out of the injection point, and if there is a component of the gradient US along the surface, then the vector potential, the vector product is non-zero, and therefore I have the conditions of the theorem are satisfied. After that, I will consider a specific example calculation of what are these currents and what are their consequences, and I'll see that there are two consequences. So instead of this simple but still more complicated device for me, I will consider a symmetric device. Here, the spin injection is from the side. Here, it will be from the bottom. There is a narrow normal film covered by the thick ferromagnetic film. Because I inject from the bottom here at this point, I expect that everything is symmetric, and the pattern of the current, which is shown here, will be sort of symmetrically duplicated. And because I assume that the film is very narrow, very thin, I will also assume that I'll expect that there will be little difference between injecting from the side and injecting from the bottom, because it's basically injection at one point. And this is the geometry which we are solving. We are solving the Bazaliy equations. We are finding the electric potential and the spin potential as a function of x and y. X is horizontal, y is vertical. And then we calculate the electric current. The electric current is given as a gradient of the sum of a certain combination of mu and mu s. So we'll call this combination capital M. And then the current is a gradient of this capital M in the F layer. So my pictures here are the representation of equipotential lines of M inside the ferromagnetic layers. The current flows perpendicular to these lines. And so looking at the lines, you see that they basically tell you that there is current flowing out and then going down. Now, the normal part is not shown here. So the current goes out in the ferromagnetic part, drops down, and then comes back through the normal. Hence the name spin fountain. There is a fountain throwing spins up, and then they fall down at the bottom of the basin, and then they flow back to your pump, which again throws them up in the air or in the ferromagnetic material. You can calculate anything from knowing M. In particular, you can calculate the vertical component of the current. Here the current goes up, and then here, or somewhere here, it already goes down. And so the vertical component changes sign somewhere, and that's where the center of this current vertex is. You can prove that those current lines are always crossing the boundary between F and N, and the center of the vertex is somewhere here on the boundary, and this is the position where it is. The currents are like a solenoid, which is infinite in the direction into the board. So they will produce a magnetic field. There will be a magnetic field produced by this solenoid and this solenoid. And this is all very nice, but our goal in particular is to explain the practical results of the experiments. And so I want to look how will the voltages measured in the Johnson-Silsby experiment depend on the position of the electrodes. So I will consider two voltages. One is measured between the top of the ferromagnetic electrode, which is wide now. In fact, I will assume the situation in the previous slide where it's infinitely wide. And the other voltage is measured between the same point, but the other point is here at the bottom, right at the injection point. And I will look how the voltages depend on the thickness of the electrode. In the Johnson-Silsby experiment, I would, the answer I find and expect is this. The voltages rise as TF increases, and then when TF over lambda F is large, the voltages are saturated and they are constant because in their case, there is no electric current. Now, in the case of the white ferromagnet, there is a current. This picture on the right is showing basically the same view as this guy, except in the horizontal plane. And it shows how the potentials, mu, how this potential, the electric potential mu, will depend on the position of the, on the point inside the device. So there is a current flowing like this. So because there is a current inside the normal metal, there will be a potential drop inside the normal metal. In the ferromagnet metal, we have the EMF, the effective EMF, and the change of mu. So that's how mu changes there. And the two voltmeters measure different voltages. One measures the difference between this point and 0, and the other measures the difference between this point and negative voltage, which is developed inside of the normal metal because the current is flowing through the normal metal. We calculate them, and this is the result. The gray area here is the one where you can compare, but it's not very illuminating because here everything is going to change. This is when the TF is comparable with the spin diffusion length. The interesting part is here, there is a difference. If you have a wide electrode where the currents are flowing, then the voltage V2 is going to be significantly different from the Johnson-Silsby, and the voltage V1 will actually start dropping to 0 as you make the electron thicker and thicker. And that's because all your currents are going to flow in the region inside the electron, and you can say that they will shortcut all the voltages were developed. So, in practical sense, when people measure voltages and they make conclusions about spin accumulations, they have to be aware that if the electrode is not very thin in this direction, then currents can develop and they will change their results, and so you have to allow for that. Now the second thing we do is we calculate the dependence of the spin accumulation of mu_s along the FF interface. So this is mu_s calculated at y equal to 0, and the red line represents the result of our calculation for a situation where the normal film is very thin, the ferromagnetic top layer is quite thick, and the numbers are given here. I'll go over them, but what is important that the spin potential or the spin accumulation initially drops very fast, and then the exponential of the drop changes somewhere in the intermediate region, and the new exponential, which is the slower decay, is dependent on the thickness of the ferromagnetic layer. If you make the thickness of the ferromagnetic layer infinite, then the drop of chemical potential along the interface is not going to develop the exponential dependence anywhere. It's a logarithmic scale, and it will be always curved. And I would like to discuss it in the next slide. So, because there are two layers here, I would want to start slowly. And I'll start with what happens in a very thin normal film without the top layer. Well, here we know what happens. The spin accumulation decays with the characteristic length, which is just the spin diffusion length. And that is shown here. In my example, which was studied, this is a big length. The normal metal is assumed to be flipping spins very rare. Then let's consider what happens if you put another top layer on your thin film. And let me assume first that this layer is similar to my actual ferromagnet, but not a ferromagnet. So precisely I will assume that the diffusion coefficient here and the spin diffusion lengths in N1 are the same as in a ferromagnet, but there is no current polarization, so P is equal to 0. Well then, the spin current will decay faster with a smaller length lambda s prime. This is because spin current can not only decay while it moves horizontally, but it can also leak up into this huge thick layer and decay there. And if the spin diffusion length for N1 is much smaller, which is the case in my simulation, then lambda s prime will be much smaller than lambda s. Now we look at the situation where we have, again, normal film, the ferromagnetic layer with a very short spin diffusion length, but it is ferromagnet with non-zero polarization. Then, this is what I find for large x. There is a decay, but this decay happens with a length, lambda c, which we estimate, or which we expand and find this formula, which is proportional to the thickness of the ferromagnet. For my thickness on the previous slide, the thickness was not very large, so it was visibly decaying. But if I make TF larger and larger, then the decay length becomes longer and longer. And eventually, if I go to the truly infinite ferromagnetic layer, the decay becomes non-exponential. You can prove that it goes as the asymptotic behavior of the decay is going to be as 1 over x to the first power far away. This is paradoxical because what you think is, look, you have a metal which conducts spin pretty well, but then you put another material, a ferromagnet, on top of it, which absorbs spin currents, which is a spin sink, and this is the jargon in spintronics, and yet the decay, you have a long-range, essentially a long-range propagation of spin along the boundary. The reason it...
Sorry, can you say something about the microscopic nature of μs? Is it a local magnetic field in ferromagnet, or some external magnetic field? Or spin potential? Yeah.
The nature is that it's a non-equilibrium accumulation. You take a piece of metal, you start with 10 million electrons with spin up and 1 electron with spin down. For a while, there is an imbalance, and that's the nature of that's measured by μs.
Okay, but it's dependence on the coordinate.
Its dependence on the coordinate means that if you inject, if you inject here, then here you have a large imbalance.
Okay.
And then they diffuse, and
it's purely diffusion
process. There is no driving force in the ball. All the driving is because of the injection. Now, the origin of this is traced to the fact that if you have an electric current which goes out, then it has to go back. And it is well known in this business that if an electric current crosses the FN interface, it produces non-equilibrium spin accumulation at the interface. So the spin accumulation cannot decay independently from the decay of electric currents. There is an interaction between them and they decay together. And then the reason why they decay slower is ultimately the fact that the electric current is conserved while the spin current was not conserved. It is not conserved. As I said, this long-range propagation is there, but it happens where the spin has decayed substantially. The initial decay is still present. So in order to detect it experimentally, you have to have very sensitive techniques. We have some other proposals how to do it, but it's a less, theoretically you could say it's an impressive result, but in practice it is about very small quantities. And here I end with my conclusions. You have generation of electric current loops inside of electrically disconnected parts of the device that modifies the Johnson-Silsby voltages, non-local resistances in a way by a factor of 2 or 3, and it leads to long-range propagation of spin along the NF interfaces. The preprint is the archive. Thank you very much.
As far as I saw in your slides, it's the model for the ferromagnet is a kind of Stoner model. So you have this polarization, and what is in your final results? What is the dependence on the polarization? I didn't see it. You saw only the general formula, but what is the dependence on the polarization? Because we can see, we can have weak ferromagnet or strong one.
So, as the polarization goes to 0, then this voltage will approach the Johnson. I mean, the relative difference as the polarization goes to 0, all those voltages will become smaller and smaller, but the relative difference between them will also increase.
So this circulating current and affecting non-local voltages also like modify these estimates for spin diffusion length. They do with Hanlon experiments and graphene and other materials.
Well, yes and no. So it is dangerous if your electrons are wide. If the width of this electron is less than lambda prime, then there will be no circulating current, and your experiment will not.
And did someone repeat this experiment and measure these 2 voltages instead of 1?
No, because we're theorists, so we're...
No, I mean maybe there is some collaborations or something like that.
The only thing which I know is that these people were worried about their voltages and they modeled it, but in their case it was not as clear as in what we are looking at, because they had all thick. This is a 3-dimensional structure, unlike our 2-dimensional. So here they inject from the one side of the electrode, and there is not only the distribution of current along the height, but also the distribution in plane. And because of that, they have this current going in and out. And so partially, what happens in their case is a very trivial result. That if you have some current flowing in and you put 2 points here, there will be voltage just because of the normal usual current, which electrical engineers know about it. It's very important for design, but not interested in physics.
Can you tell how big is internal resistance of such a contact? How hard is it to measure voltage here?
I think voltages which are measured are sort of down from the microvolt.
But can you include the shunting induced by the measuring device on the system into your theoretical model?
Well, in a way, this current is the shunting, so it is included in...
No. I mean the external shunting. When you connect the voltmeter to your...
Yeah, I understand. So you're asking about the current which actually flows here.
Yeah.
Yes, you can include that. You have to have some boundary condition here. You have to know what is the material of the wire. After that, you can include it in the framework of the simple infrared.
How large do you think the contribution will be?
That will depend on the height of this electrode. If electrode is high, then the contribution of the materials of this contact will be relevant.
Thank you.
The eddy currents you are calculating, they should produce perpendicular magnetic fields. Yes. Are they observable?
0.1 Gauss.
So that's small, right?
It's small.
And it depends on the current density how you drive this system.
Yeah, so I took those experiments where they were driving enough spin current here to actually switch a small ferromagnet on top of it. I said, well, that's probably the largest spin current one can possibly get. And then for this case, I estimated how big will be the circulating current in the infinite case. And that gave me 1 Gauss for the permalloy on copper structure.
In the spirit of the previous question, what would happen if you would apply some field out of it?
Magnetic field?
Yes.
You mean this way?
Yeah, in your spin fountain.
So, you know, I cannot answer because my whole thing is two-dimensional. I would have to have third dimension, which goes out of plane to answer your question. There will be some rotation of this electron, some cyclotron motion, and so I don't know.
Okay, thank you. So,
does the conductivity mismatch play any role here in the normal and the ferromagnet?
Well, the conductivity mismatch will result in the fact that you will probably have less ms. So then you will have less driving force and less circulating current, and all these effects will become smaller. But if you normalize everything for us at the boundary here at the bottom, then results are...
Okay, did I get you right that in your setup the ferromagnet is just a system with the initerant electrons with imbalance, spin up and spin down, but the appearance of microscopic magnetization doesn't matter?
Yeah, if you would have a material where somehow there are two different ferric surfaces for up and down, but for whatever reason it doesn't have M, you have the same routine.
okay.
I think we have to move on, so let's thank the speaker again.